I guess we started to deal with a theorem which generalizes some common result in analytic geometry. Well, if you have points, lines, planes, and if you take 2 points, x, y, and some real number r, then rx plus 1 minus ry, that's in the point, in the line, on the line, or on the plane. And well, the converse is also true. Well, we were dealing with the extension of that to affine subspaces. Now, the theorem was we took a non-empty subset M of Rn, and the result was now M is an affine subspace of Rn if and only if, no matter what xy we take in M, and no matter what real number r we take, rx plus 1 minus ry is in M. If I remember correctly, we have shown the only if part, that is, if M is an affine subspace of Rn, then we have this right-hand condition. Now, in dealing with the if part, now let us assume that the right-hand condition holds. That we have this condition, then what we did was, utilizing the hypothesis that M is non-empty, we picked then we have shown that M as a set is equal to M plus M minus M. We have shown this, right? But of course, since we do not know, and since we are actually trying to show that M is an affine subspace of Rn, we still do not know whether M minus M is a subspace of Rn or not. But when we show that M minus M is a subspace of Rn, this equality will yield the result that M is an affine subspace by definition of an affine subspace. Again, already shown. But now M minus M, that's a subset of Rn, which is a real vector space. Now, if we show that M minus M is non-empty, and that it's closed both under scalar multiplication and vector addition, this will yield the result. This will imply that M minus M is a subspace. Now, note that M minus M is non-empty since M is non-empty. In fact, we can take any point lowercase m in here, and then 0 will belong to m minus m, because you can take the same member here and here. But that we do not know. That we do not need. So, okay, this suffices. Now take any xy in M and any r in R. We need to show that r times x minus y is in M minus M again. Okay? Now, r times x minus y. But this is rx minus ry Now we can add to this y and subtract y from that. So that we have in this part rx plus 1 minus ry and then minus y. What do we know about this vector? Now, by hypothesis here, that's in cap M. What do we know about y? That's in cap M as well. So this vector is in M minus M. Hence, we have shown that for any r in R and for any xy in M, r times x minus y, that's in M minus M. So we refer to this by saying that M minus M is closed under scalar multiplication. Now let's do the same thing for vector addition. So let us take two vectors in M minus M. Take any W1, W2 in M minus M. Well, then by definition of this set, W1 is x1 minus y1 for some x1, y1 in cap M, and W2 x2 minus y2, again for some x2, y2 in cap M. Now, W1 is x1 minus y1, W2 is x2 minus y2 for some x1, x2, y1, y2 in cap M. Now what we know is, we know this, which applies to all four if we take any two together. But now we also know, already know, that this is closed under scalar multiplication. By hypothesis, now if I take 1/2 x1 plus 1/2 x2, this will be in M, because 1/2 plus 1/2, that's 1. And likewise, 1/2 y1 plus 1/2 y2 is in M. So if I take the difference of this vector in M and from this vector in M again, that will belong to M minus M. So, but I can factor this out, x1 plus x2 minus 1/2 y1 plus y2. This is in M minus M. This is not exactly, this is equal to 1/2 x1 minus y1, then plus x2 minus y2. That is, it is equal to 1/2 w1 minus w2. But what I wish to show is that w1 minus w2 is in M minus M. I'm sorry, this is w1 plus w2. That w1 plus w2 is in here. Well, I know that this set is closed under scalar multiplication, so I can multiply this by 2, and that will still be in here. As M minus M is closed under scalar multiplication, 1/2 times, well, let me write it 2 times 1/2 w1 plus w2, that's in M minus M, but this is nothing but w1 plus w2. So we took any two members from this set and have shown that their sum is in this set as well. Thus, cap M minus cap M is also closed under vector addition. Hence, M minus M is a subspace of Rn. So, we have shown that M is equal to this, is an affine subspace of Rn, which was to be shown. Okay. So this will actually simplify our life a lot. But before that, any questions about this? Let us consider the following problem. Now, when we had closed sets, the notion of closedness, well, by definition of a topology, the intersection of any non-empty collection of closed sets was closed. We took advantage of that in not taking it as its initial definition, but in showing that there is the smallest, given any set A in any topological space, there is a smallest closed set which contains that. We considered the collection of all closed sets which contained cap A. That collection turned out not to be empty because the entire space that's closed and contains cap A, well, that intersection is closed by definition of a topology, and that was the smallest closed set containing A. We decided to refer to that as the closure of A. So we have the smallest extension of cap A such that it becomes closed. If it's closed, then it stays invariant. We did something similar with convexity. Now we took any set cap A. Well, that may or may not be convex, but wanted to define the notion of a smallest set, if possible, which is convex and which contains cap A. And we decided to call that the convex hull. But again there, the intersection of any sets which are convex, of any non-empty collection of convex sets, that was convex. And for any set cap A, there always existed in Rn some subset of Rn which is convex and which contains that, because Rn was convex. So that was now. We will, and here from linear algebra we know, given any subset S of Rn, there is a smallest subspace which contains that subset. How do we refer to that? The subspace spanned by that set, say cap A, and we write span A for that. Well, the reason is again the same. If you consider the collection of all subspaces of Rn which contain the given set cap S, that's non-empty, because the entire space is a subspace of itself and contains that set. Moreover, the intersection of any non-empty collection of subspaces, that's a subspace again. Now we will do something similar with affine subspaces. That is, given a subset, say cap S of Rn, we wish to define the smallest affine subspace which contains cap S. Okay? But for that we need to check whether the same systematic holds in here, which was true for closure, convex hull, and the subspace spanned by a given set. There were two things. Well, there will always be an affine subspace of Rn which contains any given set in Rn. It's Rn itself. But now the intersection of any number of affine subspaces should be an affine subspace. Is that true? Well, that might be empty, because in R3 we have seen all points are zero-dimensional affine subspaces, all lines are one-dimensional affine subspaces, all planes are two-dimensional affine subspaces, and R3, that's the only three-dimensional affine subspace of itself. So if we take, for example, two distinct points, well, then their intersection will be empty. But it will turn out to be true that if that intersection is non-empty, then the intersection will be an affine subspace of Rn. Now let's continue then with that proposition. Let I be a non-empty set. We'll take it as our index set. Assume that M alpha is an affine subspace of Rn for any alpha in I. Moreover, assume that the intersection of these M alphas when alpha is in I is non-empty. Then the conclusion is now intersection M alpha, alpha in I is an affine subspace of Rn. Now let us show this. Now here, the non-emptiness of this, well, it implies that there is some common member, say lowercase m, to all these affine subspaces. An affine subspace will be some singleton consisting of a member of the space plus some subspace, well, which we know is, if M is the affine subspace in question, is cap M minus cap M. So let's take such an M, which is common to all these. Well, maybe we can use that as the common singleton for all subspaces in here. Pick some M in the intersection of M alphas in I, which we can do by this assumption. Now, for each alpha in I, M alpha can be written as the singleton consisting of M only, but that's the same for all alpha in I, and this, where M alpha minus M alpha is a subspace of Rn. Now, a natural approach, a natural conjecture is, now consider this whole bunch of subspaces of Rn. What can you tell about their intersection? That will again be a subspace of Rn. Will that be non-empty? Yes, because each of these contains the zero vector of Rn being a subspace, so zero will belong to all of them. Okay. Then, the intersection of M alpha minus M alphas, alpha in I, is a subspace of Rn. We now claim that the intersection of all M alphas is nothing but M plus the intersection of these M alpha minus M alphas, which will complete the proof, as this is, by definition, an affine subspace of Rn. Some singleton plus a subspace of Rn, which will complete the proof. As will turn out to be an affine subspace of Rn in that case. Okay, well, let's then show that this holds to complete the proof. Well, it's a set equality. We need to show that this intersection is contained in here, and then the opposite inclusion. So take any x and intersection m alpha, alpha in I. Well then, for each alpha in I, x is in m alpha, but we know that m alpha is equal to, this is a member of m alpha, it's common to all the m alphas, plus m alpha minus m alpha, implying that x is equal to m plus some y alpha in here. But then, for any alpha in I, y alpha will turn out to be the same member of m alpha minus m alpha, namely x minus m. Then, for all alpha in I, y alpha is equal to x minus m. Thus, x minus m actually belongs to the intersection of all these. So, x minus m, that belongs to the intersection of m alpha minus m alphas, alpha in I. Thus, now x was an arbitrary member from here. X now is m plus x minus m, but that's in the set singleton m plus intersection m alpha minus m alphas, alpha in I. So this shows that this set is a subset of this. Hence, intersection m alpha, alpha in I is contained in m plus intersection m alpha minus m alphas, alpha in I. Now, in order to complete the proof, we also need to prove the opposite inclusion. So let us start by taking any point in here. Now, take any W in M plus intersection M alpha minus M alpha, alpha in I. But then W is equal to M plus X for some X in this intersection. But then this X will belong to each of these. So, for all alpha in I, X is in M alpha minus M alpha, so that W equal to M plus X is in M plus M alpha minus M alpha, but that's nothing but M alpha itself. Because we know M alpha is an affine subspace, M is a member of that, so this is just M alpha. But what have we shown? We have taken any W in here. We have shown for all alpha in I, it belongs to M alpha, which simply means that W belongs to the intersection of M alphas. Thus, W is in the intersection of M alphas. So this set is also contained in the intersection of M alphas. Therefore, they're equal to each other. M plus the intersection of M alpha minus M alphas when alpha is in I. So, intersection of all M alphas is an affine subspace of Rn, completing the proof of this. Okay? Now, when we have a subspace of Rn, or when we consider a subset cap S contained in Rn, and when we consider the smallest subspace in Rn containing cap S, that is the subspace spanned by S, from linear algebra we know that the span of cap S, the subspace spanned by cap S, is the set consisting of all linear combinations of finitely many members from cap S. You can take any finite non-empty subset in cap S, form all possible linear combinations, the totality of them, that will yield the subspace spanned by cap S. We have a similar situation for the convex hull. If you have cap S as a subset of Rn, you consider its convex hull, Well, we already know that the convex hull consists of all convex combinations, which are linear combinations as well, but special linear combinations, convex combinations of finitely many members from cap S, the totality of them that yields convex hull of S. In fact, we have sharpened that result. Well, if S is a subset of Rn, we have shown it will suffice to take just m plus 1 members of cap S each time, form their convex combinations, put them all into a basket. That will be the convex hull. Is there a counterpart of that for the affine subspaces? But for that, let us first define the affine hull of a non-empty subset S of Rn. Now here we take S to be an non-empty set, because if you take S as the empty set, any affine subspace in Rn will contain that. Well, the intersection of them will be empty, but we did not consider the empty set as an affine subspace. The affine hull denoted by of S is defined by affine hull of S equal to the intersection of all m in Rn such that m is an affine subspace of Rn with M containing S. Let's check again whether this is well defined. Well, for this intersection to be well defined, the collection over which it is taken should be non-empty. Is there always an affine subspace of Rn which contains S? Yes, the whole space that we have noted before. So this collection over which this intersection is taken is non-empty. But is this intersection itself non-empty? Well, each member of the collection, cap M, over which the intersection is taken, contains S. Thus the intersection contains S, but S is non-empty, thus the intersection is non-empty as well. So this is not only well defined, but it is also an affine subspace of Rn, just by the proposition which preceded this. You have a whole bunch of affine subspaces in Rn, their intersection is non-empty, but then the intersection is an affine subspace. So let's note that down. Note that affine hull of S is an affine subspace of Rn itself, of Rn, and in fact, it is the smallest affine subspace in Rn which contains cap S. Why is that? Well, no matter what affine subspace in Rn which contains S you take, it will be in this collection. So the intersection over the collection is a subset of each of the members of the collection. So this affine hull of S that will be contained in each affine subspace of Rn, which contains S in that set. In that sense, it's smallest. Smallest with respect to set inclusion. In fact, it is the smallest affine subspace in Rn, which contains S. Now, we take standard results from linear algebra as given to us, but let me remind you now of, about the span. Now, let S be any subset of Rn. To span well, let me write it in full. The subspace, now we will write for that span S, spanned by S is defined as span S equal to the intersection of all W in Rn such that W is a subspace of Rn with W containing S. So it's just parallels this definition, but here we just have subspace instead of affine subspace. Now, span S is equal to the set of Cn xl such that x1, xl belong to S and C1, Cl belong to R. So we take any finite number of members from cap S, we form a linear combination of them using arbitrary coefficients, the totality, the collection of those, that yields span S. Okay? We'll use this. Okay. I guess this is a good point to stop. And next hour, we'll introduce the notion in the context of affine subspaces, which is the counterpart of a linear combination of vectors in the context of the subspace spanned by S, and also the counterpart of a convex linear combination of vectors in cap S in the context of the convex solid S. What's the counterpart? What's an affine combination of finitely many members? But next hour.